sigma notation. Okay, so now we're going to learn how to write the infinite number of rectangles limits, which will equal eventually the integral from a to b of the function. All right, so let's practice writing the sigma notation together. So if, let's say we have this original function f of x equals 2x, which is just a straight line, right? Like that, right? And we want to approximate the area from 1 to 2. So from 1 up to 2. Oh, I shouldn't have drawn this line. Okay, we just need the area under the curve. Okay, if we're gonna cut it into 4 equal subintervals, what would my delta x be? Yeah, how'd you do that? 2 minus 1 over 4, right? Oh, so it's 1/4, right? Okay. Now, what if I want a infinite number of partitions? Then what do I do? We would still do 2 minus 1, but let's say we want infinite, so we'll say n, like an infinite number of them. And n will go to, because we're going to do limit as n goes to infinity. All right. Okay. Now, we're going to do right-hand Riemann sums. So if I go right-hand Riemann sums, then I want to know the length of like a certain subinterval, which means I would go to the right-hand side, right? I would go up and then draw a rectangle over, right? And then I would go up here and then draw a rectangle over, and then up again and then over and draw a rectangle, right? So what I end up doing is I use this right hand point right here, which is 1 plus my delta x, right? So I do, to get this right hand point, I do 1 plus delta x. And for this right hand point, I do another plus delta x. And to get the next endpoint, I do plus another delta x, right? So each one I add a delta x. So for the expression of my right hand endpoint, it will be 1, which is the left part of my interval, but I add an increment of delta x every time. And then for whichever increment you want, we put a k there as the k subinterval. So if I wanted the first subinterval, I would plug 1 in for k. If I wanted the second subinterval, I plug 2 in for k. The third subinterval, I plug 3 in for k. Okay, so it ends up being, I'm going to plug my delta x in, 1 plus 1 over n k would be my right hand endpoint. Okay, now that you know where to put your partition, you need to get a y value for that. So you plug this in for your original function, 2x. So it goes 2 times, and then this 1 plus 1 over nk. That's your y value. Y value. And then one rectangle would be my y value times my base. And my base was 1 over n. Okay, so that gives you whatever rectangle you want to find. Now, if you write it in sigma notation, it would go the integral from 1 to 2, area under the curve from 1 to 2 of 2x, which is my original function, delta x, will equal, I want the number of rectangles to go to infinity. Add up all the rectangles, starting at the first subinterval and going to n subintervals. And then this is the area of each rectangle. And that's how you write the limit definition of a Riemann sum. Should we try this again? Yeah? Okay, let's try it again. So, we're gonna go from 3 to 7. It's kind of odd, right? Okay, so let's go width of one subinterval. We go, you should know how to do that. How do I do that? 7 minus 3, and we're going to divide it into n subintervals, so divided by n. So we'll make that 4 over n, right? Okay, a right-hand endpoint will be the start of my subinterval, okay? But I don't want to take 3 because 3 is my, what? Left-hand endpoint, right? I want to go 3, but then plus the increment. So plus 4 over n k, right? So that will give me the right-hand endpoint, not the left-hand endpoint. Do you see? Yeah. Okay. Now we need to figure out the y value. So we plug the increment into our original function. And then we make one rectangle. So the rectangle would be our y value times our delta x times our base. Skip I. Let's just work on regular Riemann sums. Okay, now we have each of our rectangles equations, and now we just write our limit. So limit, number of rectangles goes to infinity, add up the, starting from the, k equals the first rectangle to the nth rectangle, and then the area of our rectangles. Okay. And then don't worry about k. It's just, let's just work on writing Riemann sums. All right. What do you think? More? Let's do more. Okay. So for this one, this is 1 minus x squared. That looks like a downwards facing parabola shifted up 1. So from -1 to 1 is what we want to find. All right, first our delta x. Our delta x is, help me guys, 1 minus -1 over n subintervals, right? So 2 over n. Okay, our point is going to be at, what's our left start of our Riemann sum? -1 plus an increment k. Now we find our function. and we plug that into our f of x. So 1 minus -1 plus 2 over nk. And then if we want to write our limit, it would go limit n goes to infinity. Sum, yeah? Oh, yeah, thanks. Thanks, Zach. Sum starting at the first rectangle, going to and the nth rectangle. And then we do f of x. And then make sure you put parentheses around f of x so it's all multiplied by delta x. Okay. How do you feel? Why don't you try the next one on your own and see if you can get it. I'll help you do the graph. From 1 to 2, the graph looks like this. See if you can make the limit definition. Okay, did you finish? This is what I got. Let's see. So, limit n goes to infinity, k equals 1 to n, and then 1 plus 1 over nk squared plus 2 times 1 plus 1 over n k all times 1 over n. Did you get it? Yeah? Okay, this is equal to, well, the first one is the area is, this is equal to the integral from -1 to 1 of 1 minus x squared dx. And this one is equal to the integral from 1 to 2, so the area under the curve from 1 to 2 of x squared plus 2x dx. Okay. That's what these two are equal to. All right. Yes.
So I have a question.
Yeah.
So when we're finding the point.
This one?
Why do we always use the right hand?
Well, because the left one is hard to define because I can't start at 1. Like, I can't make an equation to find each one starting at 1. So if I wanted to, I could do 2 and then 2 minus 1 plus 1 over nk. That would give you the left Riemann sum.
Okay.
But it's a lot easier just to do it. It'll always show you it as the right Riemann sum.
Oh.
Since these are the since they go to infinity, they're going to equal the integral anyways, so they always write the notation starting from the right, doing a right Riemann sum, not a left one. But a left one would be 2 minus 1 over nk. Same thing. Yeah, good question. All right. And then the last section is, let me show you, if you don't know how to integrate on your calculator, here's how you do it for now. You know how math 8 is derivative? Well, math 9 is integral. And then you can just type this in easily. 1, 2, x plus 1 dx. And then it would give you 2.5. So that's the value of your definite integral. But this one would be what it is in limit definition notation, because your base is 1 over n, and then your increment would be 1 plus k over n, or 1 over nk, and then if you plug it into your function, it will be 1 plus k over n plus 1 times, and you simplify that, and then you times it by your delta x. So this is the summation notation, the limit definition of your integral here. If you wanted to evaluate this on your calculator, it would take I don't know how long it would take, but do you know how to get the summation? Math 0. You could go x goes to 1, and then just choose a number. I chose 100 for n, just to do 100 rectangles. Ooh, I forgot to multiply by 1 over 100. Yeah, that's a rookie mistake. And the more you go, if you put 900 here, then it gets closer and closer to your, it takes a really long time. Actual sum. You know. Okay. All right. So these three, I'll have you do in a second. But let's go backwards and start from limit definition and go back to the integral. Okay. What do you think my bounds are going to be? Somebody said 2. Why did you guess 2? The inside here, right, is 2 plus 3k over n, right? So 2 should be where we start. All right, if I start at 2, where should I end? Why'd you say 5? Good. So it's 3 over n, so we got to go to an increment of 3, so up to 5. All right, what's my original function? 3. Yeah, this is x minus 8. And then I need, this thing counts as my delta x, right? So we just write dx there instead. Okay, and if you want, you can calculate that on your calculator and you'll get 15 over 2. Okay, let's try this one. What's the start of my integral? -2, because it's -2 plus 5k over n. Then it ends at 3. Good, because we got to go up 5 to get a width of 5. And my function?
X minus 2. X minus 1.
Yeah, with a 5. And then this is my delta x, right? My width. So my value is, if you do it in your calculator, also 15 over 2. Weird coincidence. Okay. The 3 came from, because if I got to go from -2 and I got to go an increment of 5, then -2 plus 5 is 3. Right, so -2, and then you go -1, 0, 1, 2, 3. Okay. Yeah. What's my starting of this area? -2 still. And then I'm going up till 0. Good, because I got to go an width of 2. And then my function and my delta x. That value, if you compute it, ends up being 2. Okay. For the last few minutes, if you get it, then you don't need to do these 3 and convert them to limit as n goes to infinity. But if you want to practice and do them, then go ahead and practice and do them. But I'm going to give that time for you to figure out what you need to do. All right? In 1 or 2 minutes. 05.
Yeah.